Good afternoon, everybody. Welcome, distinguished guests, faculty, students, friends, to this very special event, the 6th Annual Ernest S. Koo Distinguished Lecture. Each year, the Koo Lecture brings an outstanding leader in technology and engineering to our campus. Actually, starting this year, we might have, some years we'll have two, I think, we'll have two of these lectures in a year. Intel co-founder Andy Grove presented the first lecture, followed by a series of eminent leaders in engineering. I'm delighted that we are continuing that tradition of excellence today with our 2017 Koo lecturer, Zishang Li. This I'll return to tell you more about him, but let me just tell you about the series. The series was endowed through the generosity of Ernie and Bettine Koo, who have been truly exceptional citizens of our College of Engineering community. A professor of ECS and a trailblazer in the design of integrated circuits and systems, Ernie was a former dean of our college and a national leader in engineering education. I'm so pleased that Bettine and members of the Koo family, right here in the front row, are here with us today. Bettine, this is a wonderful annual lecture. It's a lasting addition to Ernie's remarkable legacy at Berkeley. Now I'd like to invite Ted Koo, Ernie's son, to say a few words. Ted, please.
Thank you, Shankar. Good afternoon and welcome to all. I just wanted to say a few words about my late father and why my parents decided to establish this distinguished lecture series. My father was born in Beijing and he grew up in Shanghai where he lived until he was 19. And he came to the United States to attend the University of Michigan to study electrical engineering at a time when the United States was very welcoming of immigrants. He then finished his graduate degree studies at MIT where he received his master's and his PhD at Stanford before going to work at Bell Laboratories. He had a wonderful opportunity to come to Berkeley to join the faculty here in the EECS department. And he became part of the Cal and Berkeley engineering community for almost 60 years. And he enjoyed every aspect of his life here at Berkeley, including, of course, the research that he conducted in integrated circuits, computer-aided design, working with other distinguished faculty both here, elsewhere in the US and abroad, working with industry leaders, and leading the department as chairman and then the college as dean of the engineering school. But what he really enjoyed most was teaching and mentoring students. In fact, he taught about 4,000 undergraduate students during his career and 40 PhD students, many of whom became leaders in both academia and industry. In 2011, my parents decided to establish this distinguished lecture series really for the benefit of the Cal community for all that they had received in terms of their life and the richness within the University of California, Berkeley community. But they really established it for the students to learn from leaders and gain interesting and insightful perspective and insights from leaders who talk about their career and their endeavors. So I would just like to quote a very famous tennis player, which, by the way, was my father's favorite sport, Arthur Ashe, who was a world champion, but he was also an innovator, a philosopher, and a leader. And one of his many quotes is about life and is something that my father lived every day of his career. And it says, "From what we get, we can make a living. What we give, however, we make a life." And my brother and I would just like to acknowledge my mother. And we would also like to thank the College of Engineering and Dean Sastry for his leadership here at the school. And I'll turn it over to Shankar to formally introduce Dr. Li, which we are so pleased and excited to have here. Thank you.
Thank you, Ted. And we are also delighted to welcome members of our Dean Society today. And we just want to say your support of the college, along with that of the Koo family, is critical to continuing the mission of the college, which is educating leaders, creating knowledge, and serving society. It's never been more important, and believe me, we are incredibly grateful to this community that Ted alluded to, which is helping us through these challenging budget times. Now, back to the lecture. This year's Koo lecture is co-sponsored by the Engineering Student Council. So Engineering Student Council is the umbrella that actually oversees and coordinates over 50 student groups. And so it's basically the group. The president is, he was here. Where are you? There he is. He's in the back there. He's usually in a tie and suit, but he's wearing the Berkeley Engineering shirt. But they are sponsoring it as one of the key events for this year's E-Week. You know, the E-Week is this week, and it is. This is one of the big events out here, and so our thanks go to the Engineering Student Council for having really embraced the Koo lecture as part of the E-Week activities. I also want to acknowledge and thank members of the UAV Club at Berkeley. There they are, that's their logo, UAVs at Berkeley, who have helped with the preparations for this lecture, and I think are also using some of Zhishang's drones, the Phantom in particular down there. So thank you all for your help, Engineering Student Council and UAV at Berkeley, UAVs at Berkeley. So congratulations to the student group. There can be no doubt that innovation depends on a smart, diverse, and technically proficient workforce. How we educate that workforce, and in particular engineers, has changed substantially from my time as a student. Our challenge now is to teach engineering students how to work in interdisciplinary teams, to iterate designs rapidly, to manufacture sustainability, and to combine art and engineering, and how to address global markets. This challenge to reshape engineering education was at the center of the discussions Paul Jacobs, our advisory board chair, and I had, and that led to the creation of the Jacobs Institute for Design Innovation, which just opened a year and a half ago. Few people have done more to help that challenge than our Koo lecturer, Berkeley alumnus Zhishang Li, who I'm delighted to add has also recently joined the board of the Jacobs Institute. Zhishang received his BS degree in electrical engineering and economics from Carnegie Mellon University, and his MA degree in mathematics and PhD degree in electrical engineering and computer science from Berkeley. He worked as a research scientist in the AI lab at MIT and as an assistant professor in the robotics and manufacturing lab at the Courant Institute at NYU. He has received the National Natural Science Award from China, the University Scholar Award from Carnegie Mellon Institute, the EI Jury Award from Berkeley, and several research initiation awards from the National Science Foundation, to name a few of his honors. He joined the faculty of HKUST, Hong Kong University of Science and Technology, where in 1992, and he co-founded the Automation Technology Center and the Robotics Institute. Before I tell you the second half of his life, I should say that in the discussions that Ernie had around putting together this lecture series, he said he wanted to see people who came who were uncompromisingly strong academics, but also had a taste for business and the management of technology, innovation, and entrepreneurship. And this really stuck in my mind as we started thinking about people. And we consult pretty extensively with the Koo family as we come up with our slate of candidates to do this. And so I must say that Zhishang has a remarkable record of success as an entrepreneur. He'll tell you how this happened, from this uncompromising commitment to academia first. but he has now co-founded several companies, one called Google Technologies. Google spelled I should say the correct way, Googol, Google Technologies. That's the correct spelling of 10 to the power 100, which is a leading motion control company, a seller of robotic solutions in China. Clearwater Bay Venture Capital, that's where HKUST is located, and the Hong Kong X technology startup platform. And I'll save the best for the last, which is DJI, which is the world's largest manufacturer of drones. I think they sell more than, I don't think they tell us publicly, but at least 2 million drones a year. And the next in the business is a few orders of magnitude less. So that's we are proud to claim Zhishang as one of our own and to be the Koo lecturer this year, and honored to have him back at his alma mater. Please welcome Zhishang.
Thanks, Shankar, for the introduction. Yeah, it is indeed a great pleasure to come back and see so many familiar faces. Okay, and you know, those Shankar was my advisor, and also saw Felix, who signed my you know, course approval sheet when I first landed in Berkeley, and also Professor Jing Wang, who was the head of the department. And of course, you know, lots of things that, yeah, to me, my thesis committee members and many teachers here. So I think, you know, today, you know, I'd like to share with you that a lot of the things that I was able to do were, I think, credit to, you know, the people in the audience and also from Berkeley, you know, in many, many different ways. And so I also hope that something that I'm doing could be of some help to youngsters and the young students of you know, the next generation. Okay, so I think I happen to have a picture with Professor Ernie Koo. That was the 10th anniversary of the jury award, I think, organized by Professor Jing Wang. Okay, and Ernie was there, yeah, young Professor Shankar Sastry there, right, and Jitendra. Okay, so you all see this, and even though, yeah, I was in the system group, and Ernie was in the microelectronics group, but my roommate was a student of Ernie, so I heard all the gossip of Ernie's research group. And he was also later the advisor to the Department of HKUST and also School of Engineering. And in fact, our new dean was also a PhD student from Ernie. So you see the interaction and the connections from Berkeley with, you know, things that I do even later, you know, after I graduate. So, okay, so I'd like to probably share a couple of my own experience in connecting what I learned in college, in, you know, graduate school, and also what I'm able to do later on in my career. Okay, and of course there are also, you know, struggles and you know, positive and also some regrets, which I also like to share with you. And so this is a short outline of what I like to highlight. So yeah, a brief review of my own education journey. Okay, so really, you know, I grew up during the Cultural Revolution. Okay, and so I had basically no formal schooling until, you know, the end of the Cultural Revolution. So I had probably only, you know, that was 1977, 76. Okay, but I was very good at memorizing things and also, you know, taking tests. Okay, so I was fortunate to get into college. Then also, come to CMU for my undergraduate study. And after that, come back to Berkeley for my master and the PhD. After a couple of years at MIT, NYU, I went back to Hong Kong and working at HKUST since then. Okay, so I think this has been more than 38 years. Okay, and of course I still see audience who graduate from here 45, right? So so somewhere in between. Okay. So I like to highlight a few kind of spots that I still remember and that had impact, on myself. Okay. So for my undergraduate study, I mentioned that first exposure to modern education, but still somewhat traditional. I'm good at taking tests, getting good grades. Okay. But no experience at all on hands-on stuff. So later on I got into robotics. A reason was I took a course, okay, around 1982, but could not understand a single thing because I never seen a industry robot. And also I was, just memorize something didn't help, okay. So then fortunately a year later, I spent a summer intern at the CMU with Mark Raybert on, like the robots, okay. So that gave me a little bit of help. But overall, yes, for my 4 years, I didn't find a problem that I really want to work on, okay. So that even dragged me for 2 years, at Berkeley. I first worked on geometric control with Shankar, and because of a seminar by Isidori and by Warren, I learned some geometry, but still I didn't really have a feel for the problem. Okay, other people do, but I don't. So then I was, Shankar wanted to start a robotics program here in Berkeley, so asked me to help organize a graduate seminar, okay, in robotics. So I invited a couple of people, and they get interested in multi-finger hands because I have a pair of hands, so I could see the complex relation of the hands and how to manipulate. Okay, and of course, to have a experimental setup is very expensive at that time. Okay, so I had a fellow graduate student by the name Brad Payton. He said, if you don't have an experimental setup, perhaps you can prove it. So I learned that perhaps there's an alternative approach besides a experimental approach, which is just like theoretical physics versus experimental physics. So then I jumped into it, tried to learn the tool, and thanks to the richness of resources from Berkeley, outside the EECS department, there are so much, in addition to that, tools available. I took lots of math courses. Those are probably students there, they will still recognize those are the numbers, right? And they also have, wonderful graduate students, over there, and also wonderful professors. You can walk into their door and, asking questions anytime, right? So this, I think, I truly benefited, okay, from interactions with fellow students, with professors there, okay. And of course, I still remember, okay, this, that was, probably, yeah, when Jing was the department head, right? That department was organized into two major parts. Okay, I remember CS, but of course the CS was still a small portion, right? And the majority of was system and microelectronics, and those are professors that I know. And of course, system and the CS was, had a tremendous impact academically. Okay, but around that time, it was really the age of microelectronics. They were both, impact academic and the industry-wise. And also, lots of my fellow students from the microelectronics, after PhD, they went on to found venture, their own business that I call the PhD-driven startups. Okay, and I had 2 to 3 years short stay at MIT Leg Lab, and Mark Rabert was my advisor both at CMU, later at MIT. And after many years of being a professor at MIT, he quit. Okay, and they founded Boston Dynamics. And I asked him why, and he said, as an engineer, you really need to push from basic research, applied research to business. Even though to the day, he still did not sell a single or one, just one robot. Okay, but I think I talked to him, but he had no regret that he took it away, and the company we all know was bought by Google, and Google probably wants to get rid of him. Okay, so and then of course Jack Schwartz used to be a mathematician, and I know from his heart he wants to do something real. Okay, so he established the robotics lab. And also, I had the interaction with James Stemmel, who are back to Berkeley, and also Paul Wright, learned a few real problems, okay, on computer-aided inspection and also manufacturing, okay. So then I went back to, Berkeley, to HKUST, and these are some of the pictures of the university, okay, very beautiful, and so began to learn how to use, theoretical tool and also experimental tool. But so I established the test beds and the, on hand and also on 5-axis machine. And actually, that project was, approved by Professor Jing Wang. Okay, so he may not remember. Okay, so and then for my later PhD students, I immediately ask them, you have to learn the math and also do the experiments and use both approaches to try to solve this problem. So I think after a couple of years, I believe that I kind of know how research and also, experiments work, okay? And until, I finally utilize the controller I built for the hand for my first startup. So that is really the first part of my story, okay? So the second part, I thought I still want to, recall a few of the, important elements that I learned, in Berkeley that benefits, for a long time, okay, many of the things I do. So that is geometric robotics. I know that, here the robotics program is getting much, bigger and also much more interesting, okay? But I think the tools are still probably, more or less, I think, important, okay? And for us and also for people from Berkeley, we benefit from the rich mathematical environment and also the theoretical approach. And we use not just the traditional mathematical tools, the Euclidean geometry, right? For example, those are the people who contribute to the development of tools. And today we know, if we have a space that is modeled by Euclidean space, then you can use, calculus to analyze properties of your system on those spaces, right? Because all the engineering problems through approximation or linearization eventually become a function on Euclidean space, right? This we all know so well. But when robotics and many other things come up, the underlying space is no longer flat. Okay, so we need new tools to see and visualize those space. And the masters who built the tools for non-flat space Gauss, Riemann, Surface Lee, Klein, and Hermann Weyl. And here in Berkeley, we see so much influence of Professor Chen and Jerry Marsden. And here, the engineering and the math are closely connected. Jerry serves as the bridge, and also a number of other professors between math and the engineering. And we were so, and of course, all this is in Math 214 and 240. I just looked at last night. They are still the same numbers. Okay. And of course, the use of mathematical tool in the old days to analyze the mechanism, analyze the problems of robotics. Those are the, if you use the traditional mathematical tool, those are called the screw theory, which I call the classical mathematics for robotics, and those are the developers. Okay, and for me, I'm so fortunate I'm able to learn the modern tools. Okay, and that was introduced, of course, in the early days by Roger Brackett from Harvard. Okay, and Shankar brought me the PhD thesis by Montana, and also so forth, and also the group from East Coast and the West Coast not only collaborate but also compete in very friendly manner. Okay, and here Shankar and also many of the students that we apply and we develop the tool to robotics, to 3D vision, and also to many other interesting things. So all those, I believe, are in those courses, right? If you take EE 125, 192, and also you will see. So I think because for me, I haven't, it took me a long time to see those problems. Okay, I think the problems are really, really important. The tools, comes next to it, and now you have also AI, machine learning. But I think the problems are still the first order issue. So I like to quickly go through some of the problems that those tools are extremely useful. Okay, so for example, how do you describe rigid body motions? Okay, using those mathematical tools, and they are kinematics, trajectory. So I think when you take the course, you are going to see those are fundamental for drones, for robots, for mobile robots. Okay. And also for interconnected rigid bodies, such as industry manipulators or manipulator under constraints, right? And you need the right tools for you to visualize the kinematics, the inverse, the Jacobian, all those. Okay, and they also for multi-finger hands, which was my favorite subject for many, many years, and all those grasping force model optimization, okay, contact modeling. And they also for parallel mechanism, okay, manipulators, okay, like all those for high-speed pick and place, and for their variety of problems. And they also for lots of biomechanical systems, like the shoulder joints, the eyeball joints, and all those. How do you model them? How do you analyze them? Planning, control, synthesis. Okay. And they also for machine design, some critical components underlying vehicles, 5-axis machines. How do you model those extremely important components? Okay. And they also for non-holonomic motion planning. And when we worked on this problem, we didn't know today autonomous driving is become such a big popular subject. But around that time, we just want to understand a few things. How do you manipulate an egg? How do you understand a falling cat? How do you understand parallel parking? And many, many years later, the theory, the formulation all become a real practice. Okay. So, and also, for places I come from, where probably 80% of the world's smartphones are manufactured there. For such high precision gadgets, how do you specify the tolerance, control the tolerance, and they also do inspection using automated setups. So again, they are in the same setup. and also for workpiece localization to automate industry production line. This today we call Industry 4.0. Okay, so those are the issues, and also for today that you need multiple arms to work together. How do you model such kinds of systems? Okay, and those are also problems of importance. And also, like this is a setup where the motors for the drones are assembled. Okay, and there are lots of calibration issues and also testing issues. And also using 3D sensing and workpiece modeling, offline programming. Okay. So I think I give you, some of the students, if you are going to take those, robotics or related courses, those are the building blocks, okay, for a variety of, technology or robotics applications. And if you have those mathematical tools, you will see, much more clearly, okay, the fundamentals of those problems, okay. And of course, I then move on to the next part. So, and of course, in Hong Kong, when I joined the university, used to be a labor-based manufacturing. Okay, there was no need for automation for robotics. Okay, so how do we move out from the laboratory to build a new industry, because we cannot wait for something to happen? I think the best thing is to create this industry. And one of the motion controller cards that we built was accidentally utilized to save a production line in China. Okay, so from that experience, we try to ask a question. How do we use the technology to benefit the ordinary manufacturers? Okay, the best way is to start up a company. But around that time, there were no policy at all, governing how do you move the IP technology from laboratory to factory, okay, to spin off. And we were so fortunate that Jing Wang, again, was the VP R&D at HKUST, and Professor Pinko also used to be a professor from this department, was the Dean of Engineering. And they help to define the policy at HKUST for technology transfer. And today, I go to many universities and places, and no place has a policy that is as so supportive to this effort as the policy we have in HKUST. Okay, perhaps Professor Jing Wang can tell us a lot more how he did it. And the second thing is we need a place for interacting with the manufacturing industry in China. And HKUST, under the leadership of our first president, Wu Jiawei, with the Shenzhen government, established a incubation facility in Shenzhen, allow our students and the faculty to work there with the massive manufacturing industry. So those are the elements that are needed to put everything together into something that happens. Okay. And today, of course, Google Tech is the largest motion control company in China, and we help to build a manufacturing equipment, machinery industry in Shenzhen and across China. Okay, so those are some of the products that we manufacture. And it's being utilized in more than 60 different sectors, and especially as the country moves to Industry 4.0, this provides the foundation for it. And through this example, I said I learned a lot. Okay, not just how to run a business, but how do we prepare our students so they become very competitive in this innovative process. So I was fortunate to teach a course, okay, a robot design course, okay. And this course takes place over a period of 8 months. And the students are, grouped together from different disciplines, mechanical, electrical, computer science, or even math department, okay? So they work intensively together to design, build, and they also iterate, fast for several robots to engage in a competition, okay? And so they learn all the things that a system designers need, okay? Project management, time management, system, hardware, software, electronic design. And also in order for them to speed up the process, I bring the students to Shenzhen, where they can buy the components, they can make the PCB, they can, do the, the metal machining much faster than if they do it at the university, 5 or 10 times faster. Okay, so this way allow them to not just win the competition, but also to understand the manufacturing ecosystem in Shenzhen. So from that project, a number of students emerged to be an entrepreneur. Before that, they will probably go to work for finance, go to work for big companies, multinational companies, and since then, the picture has been more or less changed. And those are the students who, continue on to found their companies, including, Wang Mingyu, a kind of electrical outboards company, and Wang Tao, a DJI, and also industry robot company. And of course, here a little bit, sidetrack. When, Wang Tao asked to do a final year project, okay, in drones, because he loves, helicopter, and to fly helicopter was difficult. And he said he wanted to, make that process easy, to build a autopilot. I said, you are crazy, because in order to do this, you need, probably big lab, big budget. Because I took, those are the people who are able to do, Takeo Kanedi from CMU, and my professor in Berkeley, right? And Vijay Kumar from UPenn, right? So they have big labs to do this. And I said, you have only 3,000 Hong Kong dollars. This is only, 500 US dollar. This is not possible. But nevertheless, he, kept on doing. So he, after the course, he, built a very ugly autopilot for the drones. And then, he continued his master's study with me, but just to, get a little bit of stipend so that he can continue his effort. He set up a company called the DJI, hope to sell a few autopilot to the hobbyists out there, okay? And then the, quadcopter arrives, then he switched to quadcopter, and eventually, the Phantom that you see over there. And there was a little story behind the Phantom, okay? Because, we found out lots of the autopilots was used by, DIY, who, use a GoPro camera and the DJI autopilots to do aerial photography. So then we went to, Silicon Valley to talk to GoPro, made a proposal, see if we can collaborate with them. And the GoPro founder said, okay, fine, yeah. I mean, I love your stuff, and let's do it. And here is a proposal. You get 30% of the profit. I get the 70%. So, for, design, manufacture, everything. He does the marketing. So we kind of, around that time, that was the normal. Because if you look at how Apple distribute, Foxconn in the manufacturer of Apple only gets 2% of the profit, right? Giving you 30% was pretty generous, okay? So, but then we kind of, are we going to, stick with the status quo, or are we going to do something different? So I was fortunate to find a Berkeley alumni who happened to have a company providing the chipset to GoPro, but he could only give us a low-quality chipset. So then, I got, other students together. So they built the camera in 3 months. They learned quickly how to design and build something new. And then the Phantom was the story. Okay. So today, DJI is a much bigger operation than GoPro. So, and also the Phantom received the top 3 gadgets of the year by Times Magazine, and also the Inspire, also the number 2, and we beat Apple in both places. Okay. So I think that is the story, and highly recognized as the first high-tech product from China, which a few years back was only recognized as a copycat. Okay, I think it changed the history, okay, of tech industry in China. And Michael Morris, I think, I probably show you a video, not just for taking pictures, but also applications.
When DJI launched the Phantom, we changed the world. With every generation since, we've made flying easier, more reliable, and smarter. Now, we are bringing this expertise to the world of agriculture with the DJI Agras MG1, the first agricultural aerial platform designed for ultimate effectiveness, industry-level reliability, and precision spraying. One single Agras MG1 can carry 10 kilograms of fluid and cover 10,000 square meters on a single charge, 40 to 60 times faster than manual spraying. The Agras MG1 is dust-proof and corrosion-proof. It's also water-resistant, so at the end of a spray, it can be rinsed clean. Its extreme reliability is possible through a specially designed internal cooling system. Air enters from the front, and mist, dust, and large particles are filtered out before reaching the motors, where heat is then dissipated into the surrounding air. Industry-standard ceramic nozzles come pre-installed and can be swapped out if necessary. Spray quality is further enhanced with a downward-facing radar that keeps the Agras MG1 at exactly the right height above the crops. Using the Agras MG1, modern farms can spray faster, more accurately, and more efficiently, bringing the DJI-powered aerial revolution to agriculture. With the Agras MG1, we are building the world of tomorrow.
So the picture that you saw, in the old ways, each year China about 20,000 farmers die from poisoning. Okay, and now with the drones, you no longer have that problem, and the efficiency you improve by more than 100 times. Okay, 100x. So the DJI set up an example, and the first impact was in my own lab. And now my students, they all group together, try to find a problem, and then work on a problem. So the second project was a group of students who want to design and build industry robots. Okay, and of course, it took us a few years to understand the right market, the right product. Because before we started, there were already big players in the industry, like ABB, Kuka, Yaskawa, Fanuc. Okay, and how can a 3 or 5 student team to get into this industry and compete with such the bigger players? So then we saw another industry which is called C3, manufacturer of your smartphone, computers, and the consumer products. This industry is 4 times bigger than the automotive industry, and there are no industry robots that are capable of solving the problem, the precision and all those. And Foxconn employ more than 1 million workers to assemble, testing the handsets. So we are hoping to revolutionize this industry using a new generation of robots. And this is another project team, follow the same path line. 3-4 students together, taking the competition project, and then final year project, they decide to build electrical outboards for surface vehicles. Okay, and after a number of trials, and they finally get a product that match the market requirement, and it is on the way to open up. So those are the experiences that I had with some of my students and also postdoc. And we were fortunate enough to be able to be next to Shenzhen and Dongguan, which has a nickname being the Hollywood of makers, in the sense that you get all the suppliers of components, all the contract manufacturers, big and small. So you can do the design, do the prototyping, do the scale up just next door at a speed that probably is 5 to 10 times faster if you are, than if you are doing here. Okay, so that is, important. And also we learned that this kind of resource, the experience that we went through, could be beneficial to other students, not just from Hong Kong, from China, from US, and also elsewhere. So we decided to set up a robotic incubation facility in the heart of this region. And any student teams, if they are interested, to pursue their idea further, they can come to us. We provide them some of the components, the supply chain, and also the needed funding to, so that they can propagate their ideas to a final product. And over the last year and a half, we have taken around 25 project teams. Some students come in with no idea what they are going to do. But in a year and a half, you're just so amazed how much they are able to progress, okay, using mentorship support under the facility over there. So those are the different types of startup groups. Some 1 people, some 2. Okay, and in year and a half, they probably develop to 10, 20, 30 students. So I think from those lessons, I said I learned a lot. Okay, so probably now with all the lessons learned, come back to see how do we redesign our curriculum, okay, for students. So this is my own challenge. Okay, here is a pipeline, right? You spend 4 years as college students, probably 2 years master, PhD, multiple number of years, then probably either go to work as a faculty or go to work in a bigger company to gain some experience. And for Mark Raybert, I counted from his undergraduate year to his first startup. It took him 23 years. Okay. And for myself, it took me 21 years, okay, a long journey. And for Wan Tao, took him 6 years, okay, and also the many student groups, right? So a fundamental question is, can we redefine or redesign our engineering curriculum, right? So students are prepared to launch their first tech-based startup right after graduation, okay. And of course, we have seen people who are capable of doing this, right? And perhaps Steve Jobs, his university did not have the right kinds of program. Otherwise, he probably could have stayed, right? And those are examples, but I don't think at around their time such a program exists. And I was pretty impressed by the guy, Joi Ito, MIT Media Lab director. So a couple years ago, he made a trip to Shenzhen. He went to visit Foxconn, DJI, Huawei, and the bigger, those hardware startups. And he come back and he completely changed his principle. Okay, he said before, Media Lab had a motto, which is said, demo or die, right? In comparison with publish or perish, right? Because they have big companies. If you prove a demo, then big companies will take it over, convert it into product. And he found that efficiency is very low. Okay, many things simply stayed in the lab. Okay, and the idea is that with advance in hardware, Moore's law, internet, and the hardware, software manufacturing tools today available, right? And also customers moving from government, defense, military to consumer. The whole picture has been changed. It is possible that small group of students could be able to move from what they are doing in the laboratory, small hobby project into product, deploy or die. Okay. And of course, in order to do that, you have to understand, learn how to learn, right? And also the mindset, he said, campus over maps, right? So in the old days, you spend lots of time, effort to build a map. But nowadays, if you have a problem, you know the objective. You just bring your smartphone and they give you the direction, will navigate to your final destiny. So a lot of things has been changed, okay? And of course, that is now the lean startup cycle. I'm sure that if you take any of the business course here, they will teach you how important, right? You have to iterate fast, right? Before your resources run out, okay? And of course, as Shankar just mentioned, the founding principle of the JECPAS, right, is to, in order for you to do that, we have to prepare our students to learn how to work in multidisciplinary teams, how to iterate designs rapidly, how to manufacture sustainably, and also combine art with engineering, and also address global market needs, right? So, and of course, this is the famous Krebs circle of creativity. You combine art, science, design, engineering. But how do you combine? You have to have a purpose. The purpose is entrepreneurship, right? And the vehicle to do that are the projects allow you to, move on, okay? Even just to understand, the scientific principles. So, and of course, there are lots of, effort, examples, moving in that direction, including our JECPAS Institute, and also the Olin College model, which I went to look at, of the 24 courses you take, okay, 20 of them are project-based, okay. And also, I'm working with Guangdong University of Technology to set up a robotics school with this objective in mind. And we take students from design, mechanical, electrical, computer science, and math together. And then across, in addition to the traditional curriculum, which also we change so much. And also we introduce 8 comprehensive projects, okay? So they work together on something very specific, okay? And after that, they have something similar to what Frank Wang and those kids are doing. So those are some of the photos. I will not say too much. And so I finally like to conclude. And again, no better than the fundamental principles behind the founding of the JECPAS Institute. This is what we try to get into. And of course, from my own experiment or my own experience, we have first had, have a problem, have a purpose, okay, and then form multidisciplinary or even multicultural teams to work on those specific projects. But don't stop at the project. Don't stop with a degree. Okay, you move on from design to deployment. Okay, that is, my final lesson. Thank you.
We'd like to take some questions from the audience, and as always, we give preference to students. Small price to pay. Tell us your name, major, all of that. Any
Hi, my name is Brunston. I'm a first-year EECS major, and my question for you, Professor, is what did you find to be the most difficult thing in starting Google Technologies as well as DJI in terms of the startup process itself?
Yeah, I think as I have gone through, is the team. Because, DJI took several, had to be rebuilt a number of times. because he didn't, in the beginning, have the right team to start with. And the course, the curriculum, now we are designing, and also with Jacobs, Institute, just the right kind of opportunity for you to build your team in the very beginning through your course project.
Hi, I'm Griff. Wow, that's loud. Hi, I'm Griff. I'm a third-year EECS major, and I wanted to ask you, what advice do you have for people who maybe don't have a lot of experience in that region, Southeast China, East Asia in general, but are interested in tech in that region?
Yes. So now we have a team to help people from outside Hong Kong, China to do this. Actually, we are working with IEEE Robotics and Automation Society to run a boot camp in the summer. Okay, and also, I'm talking with the Jacobs Institute to perhaps set up joint courses so that our students, from China, Hong Kong, and the students from Berkeley can have opportunity to work together in a joint course and also to explore both areas. And we had that last semester with National Seoul University and also Tsinghua University with more than 60 students. Yeah.
All right. Let me take my microphone. Sorry. Zishan, this has been a fascinating afternoon with you, as we knew it would be. On behalf of the college, we'd like to present you, and this is the President of the Engineering Student Council presenting it to you, with a small remembrance of today's event. It recognizes our deep appreciation for your commitment to engineering education. Many thanks to you. Thank you also to our co-sponsors, the Berkeley Engineering Student Council, and especially to Ernie and Bettine Koo for making this outstanding forum possible. Thank you all for being with us today, and go Bears!